the solutions to the refresher that I posted here. You're welcome to skip around to any of the parts of this that you're interested in getting the title in the huh, upper left over there. One of the things I might want to do is horizontally flip my camera right here. Should tell you what section I'm looking at right here. And honestly, I'm hoping that most of you guys don't need to see any of the algebra or trig stuff. I'm really almost doing this just as much for practice for me, for creating videos, writing on my with my new stylus and stuff on this digital pad here, all that good stuff. So we're going to see how this looks. We're going to see how this sounds. And again, feel free to skip around to the parts that you are particularly looking for here. But otherwise, we'll get started on walking through some of these problems here in the refresher. So we're going to start with the algebra, then we'll hit trig, then we'll do differentiation, then we'll do integration. So I'll break this down into the 4 parts. So first things first, in the algebra section, we just want to remember basic algebra because we're going to need pretty much all the algebra that you know to use this semester here. So I do want to remind you that we still do expect that you can do things like factor, complete the square, come up with equations of our basic families of functions, stuff like that. So let's take a look at our first one here. So the first thing we're looking to do is it looks like we're factoring some 8x squared plus 6x minus 5. And so we're seeing that we have an a value that is 8, not 1. So we know that we need to use the AC method to factor. A times c in this case is negative 40. So I'm going to make my product pair list for 40. 1 and 40, 2 and 20, 4 and 10. 4 and 10 looks like it'll do it for us since their difference is 6. And I do have a negative, so I'm looking at a difference of 2 numbers here. So I think that I can go ahead and rewrite this guy as 8x squared. I'm going to rewrite 6x as plus 10x minus 4x, that's my 6x, and minus 5 on the end. Now we can do a little bit of factor by grouping here. It looks like there is a 2x that is common to the first group, leaving us with a 4x plus 5. It looks like there is a negative 1 that is associated with the second group here, and that's also going to leave us with a 4x plus 5. This is how you know you did things right, if you get your matching terms right here. So I'm going to go ahead and factor out that 4x plus 5. And that's going to leave me with that 2x minus 1. So here we are, we're factored. This certainly would be the final answer if this was the question in algebra class. Hopefully you keep remembering things like re-like factored form because it tells us roots. So if this guy were set equal to 0, if we were looking for the roots of an equation, even though I only gave you an expression, here it looks like I'd be seeing negative 5/4 and 1/2 right here. Looking for roots, even if you're looking for factor form, is also a good thing because this can help us go ahead and do things like help us check our answers. If we wanted to, for example, back over and go ahead and look at our next one here. Next up, it looks like we are trying to identify the exact equation of a parabola shown. Our word of warning on this one, I want to just remind you guys, don't go being guessers this semester. I see 4 points that are little gray dots on this picture right here. 3 of them I can tell exactly what they are. The 4th one at the vertex, I'm not 100% sure. It looks like it's maybe at 3, negative a half. I would advise against you doing some guessing like that. What I can see for this one right here is it looks like, let's break this here, it looks like what I can see is that I see that we have roots at I see an x equals 2 and at 4. This is going to suggest to me that I think I can build an equation that's going to look something like, I don't know how wide or narrow that parabola is, but I do think that my factored form should look something like this. I don't know if the scaling on this could be different. It does look relatively square scaling right there, but again, what we don't know is that other coefficient sitting out front right there are constant multipliers. So let's go ahead and identify another point. I'm positive that 0, 4 is a point on this graph as well, and we can go ahead and plug this in over here to help find the a that's going to be associated with this. So 4 goes in for y, 0 goes in for x. It looks like we've got a positive 8 right here. When we divide positive 8 over to the other side, it looks like we're going to be landing at a being 1/2, and that's going to tell us that parabola that we're looking at right there, I think, is probably best described in factored form as 1/2 times x minus 2 times x minus 4. I think that's what I'm looking at for that guy there. Moving on now, numbers 3 and 4, we're looking to find an intersection and then just combine some fractions. I hope, again, that these are things that are already natural for you. I'm kind of assuming that a handful of people are going to say, oh yeah, I guess I forgot that little technique, but you're capable of doing it once you see it. So that's good here. So when we're looking for our exact values of intersections of equations, just to highlight a couple important words here, I did italicize exact because I'm not interested in decimals, so I'm not interested in just going to Desmos and seeing what the decimal values are. And we are looking for intersections. Whenever I see the word intersection, I'm certainly picturing a graph. I can see here in this case that we have graphs of, it looks like we've got a circle of radius 2. So my circle of radius 2. I also have a line. It has negative slope. It has a positive y-intercept. So I'm imagining for myself, before I go into this, 3 different possibilities. It might be the case that our line is going to be living out here. Negative slope, positive y-intercept. In this case, we have 0 solutions. It might be the case that that might be the perfect line to end up being tangent to this circle. You guys all just finished Calc 1, so this should be a believable idea to you right there, that I could have one point of intersection that we could be finding. Alternatively, I think probably what we're all kind of, in a sense, anticipating, which is a little bit more typically the case, is that it might have 2 points of intersection here. So just as far as drawing the picture goes, I'm kind of laying out for myself before I do any math, like, what do I even think this is going to look like? And I do know that we have 3 different solution set possibilities. A gives 2 solutions, B gives 1 solution if we're tangent, C gives 0 solutions if we never touch the circle at all. So it's good to stop and think. You're going to want to draw a lot of pictures before you go in and do some math this semester here. So always stop and do yourself these little bit of favors to give yourself some intuition. Now, we know that to go ahead and find intersections, we really just want to hopefully use substitution. We use elimination when things line up, but substitution is probably the more typical thing that ends up getting used here. Here, I do have one of my equations already solved for y. That's good for me. That means I can directly do a substitution into the other. So it looks like we're looking at x squared plus negative 10x plus 7 squared equals 4. And we just want to solve this guy for x. It doesn't look like it's going to be very nice, but it also looks like it's going to be a quadratic, so we'll be able to get over it. Negative 10x squared plus 7, let's see if we can do this in our heads here. Negative 10x squared is going to be 100x squared. Negative 10x times 7 times 2 is negative 140x. And positive 7 squared is going to be plus 49. That's equal to 4. We just want to move all of our terms together. It looks like we've got 101x squared minus 140x plus 45 is going to be equal to 0. And now we can just go ahead, pop this guy into the quadratic formula, and we're good. I'm not even really going to simplify this too much here. I just want to get a quadratic formula statement here. So negative 140 is positive 140 plus or minus square root of b squared. Notice here, I'm dropping the negative on the 140 because I don't care, because I know that squaring it means it's always going to be the positive quantity right there. So I guess I ditched a negative, but the negative would get squared away. So 140 squared is b squared minus 4 times a times c. I'm also going to go ahead and make a little bit of a guess as to which of my 3 scenarios I'm in. I mean, honestly, I'm just going to stop right here, but I do want to kind of tell you what other kind of like little small guesses I do for myself. So there's 2A on the bottom right there. So one of the things I want to do for myself is I want to say, am I in scenario A, B, or C over here? Did we get 0, 1, or 2 solutions? I know that I can always check that out by looking at the discriminant from my quadratic formula here. What I want to know is this quantity positive, giving us 2 solutions? Is this quantity 0, giving us 1 solution? Or is this quantity negative, giving us no real solutions? What I'm thinking right here is all I got to check is b squared smaller or larger than 4ac? Because that's where the subtraction is happening. So I'm just trying to guess for myself without actually doing the math. Is 140 squared bigger than these guys? Well, here's what I'm seeing. 4 times 45 is 180. 180 times, and this is about 100. I'm just going to eyeball this is 100. So 100 times 180. Well, what I can see here is that 140 is actually the average of 100 and 180. And what we kind of learned early in Calc 1, and honestly, we even do these problems in algebra, is that we get the most area out of rectangles when they're squares. So this is sort of like those perimeter problems where it's like, oh, you have this much fence, what should you do to make the most area? It always ends up being a square. So I'm thinking that 140 squared is going to be bigger than 100 times 180 because that's like the rectangle version of the equivalent square. Square is going to get more area. So I think this is going to give us two solutions. And in fact, if you go graph this in Desmos, I'm not going to pop over right now, you will see the picture that looks like the circle intersected by a line that looks like A right here. So it does pan out to be this guy. You can get your decimals in Desmos, but again, I'm going to care about us being able to find exact answers. So don't forget, you know how to do things like go do quadratic formula. We're all going to get over it when we have gross things like this. We don't care anymore by Calc 2. We have exact answers, and that's what we want there. So our last one here, we want to go ahead and find some, really here, man, I'm digging way back now, like at least those intersections take some math right here. This is really just adding fractions is all I'm looking for you to do on number 4. We're going to do a lot of screwed around with fractions this semester here. We're going to want to be able to rewrite things differently. We're going to want to be able to say, I know what this object is, but it would maybe be nice if I could rewrite this object to have different pieces. So we will do quite a bit of fraction manipulation this semester. So this is just your reminder that we kind of care that we are good at identifying pieces of fractions, that we're good at identifying what is going to be the nicest format to write our fractions in, stuff like that. We're going to want to be pretty confident in our fraction manipulation here. So just writing out what we got here. We just want to identify kind of what we're working with right here. I think that the smart thing for us to do right now is stop and ask ourselves, since we're just doing addition, subtraction of fractions, we just want to identify a common denominator. So I'm going to go ahead and just identify over here, what does it look like all the factors are that we have? We have an x squared at least needs to be in everything, and an x plus 1. So I'm thinking to myself, x squared times x plus 1 is my goal denominator for everything. So I'm going to go and make sure everybody has that denominator. That means I'm going to multiply new things into the numerators here as well. So it looks like 1 needs everything. So it's going to get an x squared times x plus 1 on top and bottom. Our second one just needs an x, so it's going to become 4x squared, and we get the additional x on bottom. Our next one needs nothing. It's got the whole denominator that it needs, so we just get to leave that guy alone. And our final one needs the x squared. It's got the x1, so this will be a 5x squared over x plus, everything. We got everything now. We just gave it the x squared. So we're good. All 4 denominators match. It looks like we can go ahead here and just combine the terms we got up in the numerator. I'm also going to identify over here, it does look like this guy expands to give us x cubed plus x squared. That's the only one that we need to expand. So coming back now, it looks like I only see 1x cubed, so it's going to survive. I see x squared, and 4x squared is 5x squared, minus 5x squared. So all the x squareds cancel. We never had any straight up x terms, so it looks like the constant is the only other thing that survives. So I'm just seeing x cubed plus 3 as a numerator here, x squared times x plus 1 as a denominator down here. In general, one of our things that we want to remember about fractions is that factored form is pretty much always our friend, especially in denominators here. So things like the factored form that we see in the denominator, almost always it's exactly the format that we'd like that in rather than expanding that kind of stuff. We like to think about cancellation. We like to think about factors when we think about fractions here to help ourselves out with manipulation. So again, be comfortable with your fractions here. That's going to be a thing that we'll regularly have to come up against here. So that wraps it up for the little basic algebra questions I just wanted to look at right there. So now let's go ahead and move on to some trig things here that I would like to also, let me see if I can get my zoom back to the, no, zoom in, zoom out. Both directions do the same thing. Let's see if I can get my zoom to go back. That's going that direction. Come on back now. Oh, there we go. Now we did it. Okay. Okay. Here we are. We're coming. There we go. I think that's about good right there. Might end up getting some weird mixed sizes on some of these documents here, but I'll see if I can figure out my zoom status better here. So again, Desmos and WolframAlpha, I expect that there is no algebra that you can't do or verify between those two websites right there and the experience that you already have. So make sure that you use those tools to verify all of the things that you're getting here. So let's go on now to some of the trig things. I'm just going to yell at you about the trig things that you should remember right here. A lot of trig things ends up being a lot of memorization. I know that some people do that memorizing no problem. I know that other people are like, oh, I've never learned any of my trig values. I was one of those people, and then eventually I got out my self-beating stick and I beat myself into knowing all those values. You should too. This stuff doesn't go away. By the time you're in Calc 3 and Diffie-Q, we're going to want to know these values even more than you do right now. So if you don't have all of your trig stuff memorized, make that one of the things that happens this semester. That never goes away. It's always going to be an expectation, and so we want to make sure that we're on top of this here. Gosh, I got to stop doing my scroll here. Let's look at our exact values here for some of these guys. I'm going to draw the little picture that I use to help think of all these as well along the way to kind of show you how I think about these. So sine of negative 30, when I'm thinking of all of my trig values, I pretty much always just draw myself a little tiny circle. It's not going to be much. When I'm thinking negative 30, I'm picturing that we're at this angle that's down here. I know that sine is measuring height. I can see that my height is my smaller of my two options between 1/2 and √3/2. So it looks like I'm choosing the 1/2 option since that's the smaller one. I can also see that our height is downwards here, so I attach a negative to this. So I'm looking at negative 1/2 for the sine of negative 30 degrees there. The other thing that you should remember is that the sine of a negative is equal to the negative of the sine of the positive right there. So that's another thing that, I mean, that's going to come up this semester again, some of our trig identities. So don't forget some of those things there. Our next one that we got right here is cosine of 5 pi 6. This guy's clearly in radians right here. So, all right, I'll draw a little bigger circle here. There we go. Circle enough. 1 pi 6, 2 pi 6, 3 pi 6ths, 4 pi 6th, 5 pi 6. So 5 pi 6ths looks like it's the same thing as about 150 degrees. Cosine we know is measuring the width, so we are interested in this quantity that's right here. This looks like it is the larger of the two in the right triangle that we've made. So I'm going to go ahead and say that this is the √3/2. It's the larger of the two choices between 1/2 and √3/2. And again, it looks like we're heading to the left, not to the right. So I'm going to go ahead and say that that is a negative √3/2 for this guy here. The next one we're looking at here, we've got a tangent of negative 3 pi halves, tangent of negative 3 pi halves. And I can go ahead and I can draw my circle and ask myself our lemon right here and ask myself, where am I at? So I've got negative, right? So negative is going to be negative 1 pi halves, 2 pi halves, 3 pi halves. So 3 pi halves is going to be our vertical part right here. The thing that I like to remember for myself here graphically for tangent is that what tangent is always doing is tangent is measuring the height of, given any angle, if we're measuring the tangent of an angle, tangent is always going to be the height of whatever this triangle is that's right here. This dashed line height is going to be equal to the tangent of theta in all cases right here. What I can see is going on over here is that if I tried to draw that equivalent triangle right there, this just goes up and up and up. It never hits this tangent line at x equals 1 right there. So this looks like it's going to have that infinite height. So I'm now realizing that this is probably one of those values. Maybe I should have stopped and thought to myself, oh yeah, we can't just take the tangent of everything. And it looks like these odd pi halveses are the ones where we can't go ahead and compute that answer right here. So I think this is going to be our DNE. Looks like this is one of our locations where we hit our vertical asymptote on our tangent graph out there. And I can see that because this line just goes up forever as opposed to any other angle. Eventually will intersect either the x equals 1 or the x equals -1 lines. And again, this height right here is exactly our tan theta in any angle, any circle, any triangle that we got right there. So there's our first three basic ones. Now let's look at the ones that are always a little bit more uncomfortable for people. But again, I'm including these specifically. When I made this, I was just kind of going through all of our topics for the semester and being like, what algebra things is everybody going to have forgotten that we need to be able to do? And we are going to deal with our composition of trig functions, inverse trig functions, stuff like that for integration this semester. So this is on the list of the things that we're looking to do here is deal with things like our sine of cosine inverse of a half, stuff like that. So let's go ahead and remember how we walk through these ones here. Sine of cosine inverse of 1/2. So I think I'm going to do, yeah, these two will go a little bit differently. The thing that we should start with right here is in all of math, right, if we have function notation, then we should always be evaluating from the innermost to the outermost. Whenever we have function composition, multiple layers like we've got here, evaluate from the inside to the outside. So what I'm going to do is I'm going to start by thinking about this cosine inverse of 1/2. And what I'm going to realize is that I know that angles typically go in to trig functions. And so since this is an inverse trig function, I know I should be expecting to get an angle out. So I'm going to start by saying theta is the cosine inverse of 1/2. I'm going to take the cosine on both sides to get the statement cosine of theta equals 1/2. And this is a pretty reasonable triangle for me to draw now. I can go ahead and say, well, I know what right triangle is going to do that for me if I put my theta down here. This should be cosine is adjacent over hypotenuse. So my adjacent is 1, my hypotenuse is 2. That means that this guy right there has got to be √3. I can solve for the final side. Now we come back here and we notice that what we were really doing the whole time was just sine of theta, because we named theta to be the cosine inverse. That is theta. And now I can just grab this from my drawing down here. Sine of theta in this drawing, sine is going to be opposite over hypotenuse, so it looks like I'm going to get a √3 over 2. Another thing I kind of like to do here, by the way, is just to verbalize this in words. This is like saying I took the angle, I took the cosine of some angle and got 1/2. If I were to have taken the sine of that angle instead, what would I get? And what you should be able to recognize here is that whenever we're getting the cosine of something as a half, the sine of that thing is going to be √3 over 2, give or take some positives or negatives, right? Those two are always kind of partner pairs. It's our 30s, it's our 60s out there. So this is saying I took the cosine of something and got a half. If I were to have taken the sine of that same angle, what would I have gotten? And the 1/2s and the √3 over 2s always kind of partner up out there. So let's go ahead and look at the other one here. See that it's slightly different. The reason that you should see it this next one is slightly different is because we have swapped which is the sort of forwards direction, which is the backwards direction trig function. Now we have our inverse on the outside instead of on the inside here. So we're going to do our tan inverse of cosine of negative pi fourths. Cosine of negative pi fourths here. So this one, again, if I think going inside to outside, I can just directly do this right now. I can just say to myself, well, what is the cosine of negative pi fourths? Certainly we should be picturing our circle here. Negative pi fourths is going to be down here. And what we're saying here is cosine of negative pi fourths, it looks like that's going to give me a positive √2 over 2. Tan inverse of √2 over 2. Ooh, that's going to be an awkward one right there. Tan inverse of √2 over 2. I took the tangent of something and got √2 over 2. I guess I'm not quite sure what that's going to be. Maybe this is just going to be our final exact answer right there. I guess the one thing that I want to identify right here is this. The one thing we should be careful about is that at least have this little bit of conversation right now. Remember that when we do an inverse tangent, it is always going to live in the first or fourth quadrant. This is where our inverse tangent lives right here. And I guess I should make this more like a parenthesis, like it's an end cap rather than like an arrow right there. So remember that as long as we're doing this guy, we should always be getting out angles that live always in the first or fourth quadrant. It's always going to match the sine inverse sine. So this is our sine inverse range. This is our tangent inverse range. Alternatively, if we're looking at cosine inverse, remember that cosine inverse lives up top right here. This is our cosine inverse range. We always get stuff out right here. That's because 0 to pi will get us all possible cosine values once, +1 to -1. And negative pi halves to positive pi halves will get us all of our sine values once. By combining those two, you'll see that this also then, therefore, gets us all of our tangent values once right there. It's because sine is up in the numerator right there. So it looks like this one may be a little bit of a dumber question right there, but it looks like I can just leave that maybe as my final answer right there. I don't have a better exact answer for that guy. Next up, we're looking to state the period of a couple of functions here. This is going to be really important to remember periodicity of things. Repetition is incredibly helpful all the time. It means that we only have to understand one period's worth of information, and then, in a sense, just copy that information around here. So let's talk about the period of some of these functions right here. So we're looking at Sine of x. Sine of x, we know that all of our sinusoidal trig functions are always going to have a period of 2 pi that they repeat. We are going to remember that our non-sinusoidal trig functions, tangent and cotangent, have a typical of a default period of pi. But of course, you know that we can end up modifying some of our periods here by introducing constant coefficients inside of the parentheses here. So what I like to think to myself here is we used to have to plug in all of 0 to 2 pi to get one full rotation with sine. Now, when we give our contribution of x, we're going to get our contribution multiplied by pi in the way in. So it looks like all I've got to do is give this thing inputs from 0 to 2, and that will result in, because they're all going to get multiplied by pi, that will give me 0 to 2 pi. I sort of like to think my inputs, my x values, are going to go from 0 to 2, and therefore the interior of the function is going to go to pi x less than or equal to 2 pi. So now this is me matching my original 0 to 2 pi right there, but it's helped me see that 0 to 2 is really the bounds that I was interested in to get one full period right there. So 2 is the period there. And alternatively, I think we should just be remembering that our computation in that case right there is always just 2 pi divided by the coefficient, and that's what gave us 2 right there. The reason why that's useful to remember is because right now we want to look at this sine one right here, and 2 pi kx. A little bit weird, but not too crazy. We just have our simple formula right here. This is just going to be 2 pi divided by the coefficient on x, so 2 pi k. And so it looks like our period here is going to be 1 over k in this case right there will be our period of that sine function right there. So identifying period, really important. Don't forget we can always do 2 pi divided by the constant coefficient in front of the x to find that guy out. But you should also just be able to think about this. I think that rather than having a formula, you should have a concept for this. I like to think about the intervals that we experience right there. State the algebraic expression that is equivalent to the trig expression. This is an important one. We talked about our composition of trig functions a second ago, but we most certainly are going to want to be dealing with these more in general rather than just in terms of actually computable numbers. We want these in terms of x. So this is something that we're going to have to be able to do here. So I'm looking at sine of cosine inverse of x over 2. And what I'd like to do is the same maneuver I did before. I know that we get angles out from inverse trig functions. And I'm going to move the cosine to the other side. Cosine of theta is going to be my x over 2. I'm going to multiply the, I'm going to leave this right like this. I've got cosine is the same as adjacent over hypotenuse. So now we can go ahead and draw our relevant triangle. There's my theta. Always label your theta in your triangles. Don't just draw a triangle. My adjacent should be x. My hypotenuse is 2. If you do a quick little Pythagorean theorem, that'll show you that this is going to be the square root of 4 minus x squared. If you square x squared and square this in atom, you're going to get 4, and that's equal to 2 squared, which is 4. So now I can go ahead and compute what is sine of theta, since theta is the same as cosine inverse of x over 2. Theta is what's going into sine. And sine of theta, in this case, sine is opposite over hypotenuse. So it looks like we're going to be getting root 4 minus x squared over 2. So rewriting compositions of a forwards direction trig and a backwards direction trig in terms of no trig at all, something that's really useful. It's us converting ourselves out of trig land right there because we were able to do that simplification. So always remember, we put angles into trig functions, we get angles out of inverse trig functions, and you can always just kind of make up an angle. You can always draw triangles that are associated with angles that you know and trig functions that you know. Finally, in 4 and 5, we want to identify some equations of some graphs. This is definitely a big thing that I kind of, again, expect this semester, is that you guys are going to be able to look at lines, parabolas, circles, trig functions, some exponentials and logarithmics, and just be able to say, I know that function, I can write down the equation of that. So identifying these relevant features definitely matters. So let's go ahead and look at this first one here. I'm not going to redraw these graphs, but I do want to tell you kind of the thing. I'm playing with my scroll again here. Here we go. Kind of the features that I'm seeing right here. So first of all, the first thing that I want to do right here is I want to ask myself, should I be building a sine or a cosine function? And all I see that I need to know is this. When I see that we're passing through the origin and that we are increasing through the origin, not decreasing, I know that we are looking at a positive sine function, not the negative sign, the positive sine function. The next thing that I'm going to see is that our span goes from -1 to 5, from low to high. That tells me that it looks like our amplitude is going to be 3 because we go 3 down and 3 up. That means that our midline must be at 2. So I'm going to say that our K value is going to be 2 right there. The other thing that I need to identify is what is our period here. So when I am looking at our graph over here, what I am seeing on our graph, I'm looking from the top of one peak to the top of the next peak. And I see that we're going from peak to peak. Let me just do this little thing right here. I'm looking at the top of one peak to the top of the next peak. And I see that from peak to peak right here, we went from pi halves to 5 pi halves. And that's good because that's just 2 pi. So that is a normal period right there. So that means that I don't need to make any modifications either to a constant multiple on the inside or a constant addition on the inside for our phase shift. So it looks like I think that I'm done with this one right here. It looks like I can just go ahead and say that this is going to be what? 3 sine of x plus 2 is I think that all we've got going on right there. That was a normal sine function. It had been shifted up by 2 and then stretched vertically by a factor of 3. We maintained our original period. We did not get shifted left or right. I think the next one's going to have a couple more parts in it right here. So let's take a look at this second one here. The second one, I'm going to start kind of the exact same way. The first thing that I'm noticing on the second one right here is that we are starting at a minimum. When we start at a max or a min, I know that we are a cosine function. Cosine typically starts at its maximum, right? Cosine of 0 is +1. So if we're starting at our minimum instead, then I know that this is going to really be our negative cosine function that I want to use for this guy. I know I'm going to use the negative cosine function. The next thing that I'm seeing is that this guy seems to go from, what, -6 to 2? And so it looks like they're 8 units apart. That means it's 4 up and 4 down. So I know my amplitude is 4. This, therefore, must be located at -2. So it looks like we've been shifted down 2 units. And it looks like we need to identify, I don't think that we have any horizontal shift here because it does look like we're nicely centered on the y-axis right there, but it does seem like we might have a different period here. So this one's going to be a little bit harder to identify what the period is. And the reason why is because when I'm looking at, for example, the first peak that I see in the first quadrant, it's at some weird thing between pi halves, or excuse me, pi fourths and pi halves, and I can't quite tell where it is. So what I want to do is only look at peaks where I know exactly what their height actually is. And what I'm seeing here is it looks like, all right, so I'm going to do my bad drawing right here. Oh no, oh man, not great. But what I do see over here on the left side of my, so I guess I'm picturing like this right here. So over here, this one's located at -pi. Over here, this one's located at +pi. Did I do that right? Yeah, 2 peaks to the left is -pi, 2 peaks to the right is +pi. And so what I see here is we have completed, it looks like, in this interval right here, we completed 1, 2, 3 periods were completed in 2 pi of a span. So it looks like our period here is going to be 2 pi over 3, right? It took us only 1/3 of 2 pi to complete a period. 3 periods were completed in the span of 2 pi as an interval right there. So 2 pi thirds for one of those right there. So now all we have to do is write all this information together in our function. It looks like we're going to get a y equals -4 cosine. I need to only keep what right here? 2 pi thirds. What I know is that we can do things like our period equals 2 pi over, and what do we call this usually? Like omega, right? I want to know what omega is. I know that our period is 2 pi thirds. That's 2 pi over omega. So it looks like we really just want a coefficient of 3 in there. And that's good because what that's going to say to us is since all of our inputs get multiplied by 3, we should expect a compression by a factor of 3. And that's exactly what we see in this picture. It used to take 2 pi to complete 1. Now in 2 pi we complete 3. It's 3 times faster going up and down. So I think that's going to be just a 3x in there. Again, there's nothing over here for a horizontal shift. Looks like we should have a -2 that's sitting on the end right there. Again, you should go to Desmos, confirm these guys right here. It should be pretty easy for us to play around in Desmos. I do think that, you know, if you're a little bit lost on these guys right here, our typical formatting for this is a sine or cosine of omega t minus phi. Remember, by the way, I didn't have any of these with a horizontal shift, but remember that your horizontal shift term can only be read out of this general expression if omega has been factored out. And I put t in here just as a different variable. That shouldn't matter. Plus or minus k out there on the end is our vertical shift. So vertical stretch is a, vertical shift is k, horizontal stretch is omega, horizontal shift is phi. And again, phi is only your horizontal shift if omega has been factored out of the entire expression on the inside. So that didn't come up here, but just a little thing to remember right there. So again, Desmos, Wolfram Alpha should be able to take you home on any of these guys that you're otherwise stuck on right here, or at least for answer verification. So do those things. So now let's go ahead and pop over into some of our calculus things right here. Ooh, I forgot to update our title right here. I'm going to at least change this guy to say that we're on to the calculus parts right here. That's okay. None of you guys are watching the algebra or the trig anyway. That was for me. You guys are here for the calculus parts. So let's go ahead and do that here. So calculus. So let's do differentiation. Let's do integration here as our kind of 2 steps. So so back at it here. So let's see here. All right, so let's go ahead and take some derivatives, take some integrals, remember some of the things that we want to remember. So the first thing I'm going to do is you should say these sentences out loud. I'm serious. The reason why I put things like this first is because it's pretty often the case that I end up teaching Calc 3, 50C, or differential equations. And I have people that can do like crazy derivatives and crazy integrals, but then I ask them to kind of like write out the parts to a word problem, and part of the word problem will say something like, oh, the oil is flowing out of the tank at 5 liters per second, and people can't understand that that's representing derivative information. That kind of kills me. So conceptually, I want you to remember this. The derivative is the same thing as the rate of change. If you ever see the word rate, if you ever see the word per, we are describing a derivative. That is a guarantee. The derivative measures the steepness or slope of a curve at a point. That's just a graphical version of the previous sentence. Seriously, derivatives measure rate of change. Rate of change is the slope is the rate of change, the slope is the derivative is the rate of change. The equivalent statement that you should say to yourself 47 times in the next day is the integral is the area underneath the curve. If derivatives measure slope, integrals measure area. Every time you've ever computed an area in your life, you were doing integration. Every time you ever do integration, what you are doing is you are finding area under a curve or volume under a surface or any other dimensions analog of that right there. Integrals are areas, and so that really helps us with our computing some of these, because a lot of these things we actually know geometrically. It allows us to actually kind of round about having to do calculus because areas are computed geometrically. Volumes are computed geometrically. So a lot of times we'll look to do geometry if we can, and one of those will come up right here. So first, let's just knock out these derivatives right here. I'm just assuming that you guys all haven't taken a derivative in 2 or 3 months, so just let me shout at you about some of these guys right here. We just want to find dy dx for all these guys. I'm going to go first column and then second column. I think I tried to set these up to be sort of the easier ones on the left and the ones that'll take a little bit of work on the right here. So here we go. First things first. Y equals 7. We know that taking the derivative of a constant is always going to give us 0. So I'll just say y prime here is 0. Derivative of a constant is 0. Second one here. We've just got a standard old quadratic. Nothing exciting is happening right here. When you take the derivative of a second order polynomial, you will always get a first order polynomial. That might be the only exciting thing I can say about that one. Third one here, it looks like we've got another quadratic, but we're all going to remember we absolutely cannot directly take a derivative from where we're sitting right now, or, well, I'm going to, but we need to stop and think. We cannot just take the derivatives of our parts. We need to either do the product rule, or you can expand this into a standard form quadratic and and then take our derivative the same as we did before. I'll do the product rule just because we should. I'm not even going to simplify it. The product rule, you can always label it your f and your g, and f prime g plus g prime f. Product rule is great because you really can't go wrong. You just know you need to do one derivative and not the other in both groupings. Addition's commutative, multiplication's commutative. You've got a lot of choices on the order. So the derivative of the first is 2. Leave the second one alone, 3x minus 2. Plus, take the derivative of the second, that's 3, and leave the first part alone, 2x plus 1. So that's all we got right there. We should probably expand and simplify that. I'm not going to. We're down to just a linear equation right there, though. We've got that. Let's see here. Our next one's here. I've got a y equals e to the 3x. You're going to see so many e's this semester, it's going to blow your mind. You should be super, super, super confident in doing these automatically, easily every time. We know that in general, the derivative of exponents base e, leave the entire exponent base e alone. I know that every time I take a derivative with e parts in it, I am always going to be getting back the same thing. Always. The chain rule is going to tell us that we're also going to probably get back other parts whenever there's other terms in there. The derivative of the outside function was the e to the x, and we got e to the x. The derivative of the inside function, that's 3x, is going to leave us with a 3. So we all know that we should be getting here really 3 e to the 3x for that guy right there. Right? Again, super important one right there. Next one here, we've got a little combination of some terms right here. E to the kx times 3x plus 8. It looks like we've just got to do a little bit of product rule and a little bit of chain rule right here. Y prime. I'm going to take the derivative of the first. That's going to be k e to the kx. I'm going to leave the second alone, 3x plus 8. For the second grouping, I'm going to leave the first one alone, e to the kx, and multiply by the derivative of the second, which is just 3. Again, probably some factoring, simplification we could do here. Probably factor out an e to the kx from everything right here. I don't know, maybe I'll just write this one, e to the kx. It looks like we get a 3xk plus 8k plus 3 is what we got left over right there. So maybe something like that for simplifying, but whatever. I'm worried about the derivative right now. The next one that we've got here is we've got, let's see, here we go, y equals 5 ln x over 2. And so one thing, I know that 5 does not affect my calculus at all. Constant multiples don't affect derivatives. They don't affect integrals. That guy's just along for the ride. 5 is just along for the ride. So now we just got to take the derivative of natural log of x. Natural log of x gives 1 over x. So I'm going to get my 1 over x over 2. And we're also going to go ahead and multiply by the derivative of the inside function, which should be a 1/2 times 1/2. And it looks like what we're going to get here is really, this is 1 over x over 2 is really 2 over x. And it looks like those 2's are actually going to cancel. And this is just going to leave us with just a 5 over x for my derivative. In this case right here, the 2 canceled with the 2 from the chain rule. And we're just left with 1 over x times that constant multiple of 5. So I noticed I fell off a little bit right there. But I don't think there was anything too exciting that happened right there. If you can... oh no, that didn't even just change the view of it right there. Let's see. There we go. I didn't fall off too much. There's essentially nothing that was missed right there. Okay, we're good. All right, so we've done the first column. Let's look at our second column right now and look at our ones that require maybe a smidge more. All right, next column here, I'm looking at y equals 2 sine 3x. All I got to remember here, derivative of sine is cosine. We're going to talk so much about our trig derivatives and integrals this semester. Keep these good with you. Again, 2 is a constant multiple. It's going for a ride. Sine is going to turn into cosine. Oop, come on. Cosine of 3x. The chain rule says multiply by 3. So I think I'm looking at here 6 cosine of 3x for our derivative on that guy. Next up is y equals tangent squared. So here, I think a helpful thing is to remember that when we write that square right there, that's really our outside part. That's equivalent to that there, right? So when I take my derivative here, my chain rule is going to say the outside function is the x squared function. The derivative of that is just going to be 2x. So we're going to get 2 tan x. And now we just need to multiply this guy by the derivative of the inside function. The derivative of tangent is, and I know that you remember this, secant squared of x. And I don't know that that simplifies too nicely right there. Tangent sine over cosine, that's 1 over cosine squared. I guess maybe you could write this as like 2 sine x over cosine x cubed, cosine cubed of x. I don't know. Maybe that's nicer for you. Maybe that's not. That would depend on the context. I would say, and by the way, for those of you that haven't had me before, one of the things I like to yell about, and I'll sure I'll do it later since I know a lot of you guys won't even see this refresher or this part of the refresher. I don't like when textbooks say generic things like simplify because I don't know what is simple. It depends on what I want to do with the object later. So a lot of times I'm not too worried about final algebraic simplifications. If I'm just saying do this one computation, I'm usually not super worried about what the end product looks like as long as you did your computation right. Because again, I don't know if I want to see this in terms of tangents and secants or in terms of sines and cosines. It depends on what I would then go ahead and do with that derivative. So either one of those equally good to me. I would probably, honestly, I would have just stopped at the tangent and secant because if I don't have any motivation to change it, then I don't change it. I just leave it there. So don't get too worked up with your simplifications. Then again, you should be real comfortable with making this type of simplification because there's lots of things that we're going to play around with this semester where it's going to be hard to see something in one form, but if you just do a little bit of algebra, do a little bit of trig, rewrite it differently, you're going to see a lot of very convenient relationships. So being able to change your perspective matters. Being able to just make something look different matters here. So our last three right here, it looks like our next one coming up, we got a little bit of a quotient rule right here. I do want to remind you all that we can always avoid our quotient. What am I doing here? That's not what we're doing. There we go. It looks like we're doing x plus 5 over x cubed minus 2. So remember our quotient rule. We get our low d high minus high d low all over low squared. And again, this is another great example of I have no reason to simplify this right now. It's not clear to me that simplifying is going to do anything for me right here. So I'm good with that being left in that format again. And honestly, a bit of a lazy academic thing for me as a professor. When I see your answers in that format, it's really easy to see that that's clearly coming from a quotient rule. And that's not even a grading thing. That's just a math thing. Like math people recognize the quotient rule. Don't break it out of that format, maybe, if you want people to be able to easily recognize what you're doing. I don't have any issue with that part right there. I do want to say real quick with this one, do remember that we can always avoid the quotient rule. That's a thing that people really do. We can rewrite this if we want like this and do this as a product rule with a chain rule with the power right there. That's a thing. I do that kind of a lot. And this one, I'd say with polynomials, it's maybe easy enough, but that's not an uncommon step at all right there. So remember that you got some options if you hate the quotient rule as much as most people do. The next one coming, okay, I'm going to skip the second to last, and I'm going to do the last one right now. I know I'm going to need a little bit more room for that big nasty fraction. So let's do our x squared plus y squared equals 5 here. This is a circle of radius root 5. If I am looking for, so notice this is the only one on the list that's not solved for y squared. You definitely still need to be able to do implicit differentiation. Remember that all implicit differentiation is doing is acknowledging the chain rule. So I'm going to just kind of notate here. I'm using slightly bad notation, but honestly it's better than not indicating what I'm doing at all. I'm taking the derivative of everything here. And so remember that the derivative, ooh, and I just said a bad word right there. Excuse me, I forgot a word. I just said I'm taking the derivative. What I did not say is with respect to which variable, and that is the most important thing when we're doing implicit differentiation. We want to remember that x is sort of our most base variable. Y is something in terms of x. We could solve this equation for y if we wanted to. And so remember that there are x's within this. Whether we could solve for y right now, technically we can in this case, but it doesn't have to be the case that we could. Technically we could solve for y, it would be in terms of x. So remember here, the derivative of x squared with respect to x, that's just going to be 2x. Nothing fancy happened there. But since y is an entire function of x, you should be picturing y to be this whole parenthesis thing squared of x right there. And so the derivative of the outside function would be giving us 2y. The derivative of the inside function would be, well, whatever the derivative of y is, which is the derivative of y, dy dx. I got it right there. All right, so, and finally, we're equal to a constant, derivative of a constant on the right, so that's going to go to 0. Now we're just solving for y. You should clearly notice that our 2's are going to cancel. I know you've done this exact problem before. 100% of people do this in Calc 1 right here. So it looks like we're just trying to solve for dy dx, so I'm going to subtract over x to get negative x. I'm going to divide by y, and we're going to get that dy dx here equals, we subtracted over x and we divided by y. So there's our final answer for this guy. Do remember in this case that we could have actually solved that guy for y right there. Your options are either do algebra to be solved for y, then do calculus to get to the derivative of y, or do implicit differentiation first to get the derivative of y, then do the algebra to solve. We're either doing algebra first or we're doing calculus first. And it can go interchangeably as long as you can do the algebra. In this case, we can, but we can't always, and that's why implicit differentiation is pretty convenient. That will come up again this semester, so make sure you remember your implicit differentiation out there. Finally, let's take a look at this second to last one here. It's a little bit long here for the handwriting, but I think conceptually, I hope that you all agree that logarithmic differentiation is pretty easy to think about. It just always takes a lot of writing. But the point is it's helping us make a problem easy that used to be hard. So the point is things like this, hopefully we would never actually do this using the quotient rule, product rule, chain rule. I have absolutely given like this exact thing basically as a question on a Calc 1 test before, and I have had people actually get it correct doing the quotient product chain combo. That's insane. Never do that to yourself. By the way, one thing I want to do right now is think in calculus land, roots are rarely your friend. I'm going to think of this as a 1/2 power for sure to help myself out. So we're going to do some logarithmic differentiation. What that means is I'm going to use logs, my friend logs that always help and never make things harder. Logs always make things nice for us. Logs are going to help us rip this guy apart, right? So we can use all of our log properties to rewrite this guy now as 3 ln x plus 2 plus 4 ln x minus 4 plus 5 ln x minus 5. Mistake right there. That's a minus because it's in a denominator. That is a denominator term. That's really sort of like an x minus 5 to the negative 5 if it was a numerator. So that gets the negative. Very similar. The next one gets a negative minus 1/2 because it's a 1/2 power. And that's a ln 2x plus 1. So now these are all easy derivatives for us to take. The derivative of the outside function here is going to give us 1 over y times the derivative of the inside function is y prime right there. On the right, we're going to get all of our derivatives. So I'm going to get a 3 over x plus 2. I'm going to get 4 over x minus 4 minus 5 over x minus 5 minus our 2 is going to pop out from our chain rule, and it's going to multiply by our 1/2 and cancel. So that's going to leave us with just a 1 over 2x plus 1 right there. Finally, to solve, I'm solving for y prime. I wanted my derivative, so I've really got to multiply this whole dang thing now by the original function, and we're done. So again, implicit differentiation is nice because it works out the exact same way every time. It's these same 3 lines of work every single time. One of the reasons I threw this on here, I do think that there's going to be a time or two where you're going to need to do this semester, but more importantly, I just like to think like this is just like a crafty way to do a derivative, right? So I do like this as just you should at least appreciate this technique for being like, oh, that's kind of smart. Like I see it, this is way smarter than doing this some other way. I just want you to kind of appreciate that for a second, because one of the big components of this class is going to be integration techniques instead of derivative techniques. And you're going to see some techniques where, similar to this one, you're going to be like, oh man, that's a really sweet thing that somebody figured out. It just makes that all a lot nicer for me than it could have been. And so this is maybe just more of an analogy right here that this is a complicated derivative that if we're smart and we do it careful, it's a pretty easy derivative. Even though the answer looks gross, it was easy to do. We're going to get some integral techniques this semester that aren't mathematically similar to this, but in the fact that they are crafty and helpful is going to be sort of equivalent. So we'll get some things integration-wise that in my mind are sort of like that right there. So there we go. We took all the derivatives that we were trying to take right there. Let's talk about some limits real quick. Man, these limits I might just straight up talk my way through without actually doing any of them. What you should be seeing for these 4 limits are What I see in the first limit, the most important thing, okay, actually, sorry, let me back up. All four of these limits are going to positive infinity. That's what makes this kind of a quick and easy thing for me to do. Since the limits are going to infinity, I know that I only care about the major term, the dominant term in each of the fractions. In this case, our first one has dominant terms in the numerator and denominator of x squared over x cubed. That's going to be like stuff like 1 over x to me. And so when we head off to infinity for x, it looks like this guy is going to tend towards 0 right there because the denominator is going to grow faster than the numerator. For the second example, I see that our dominant terms are 5x cubed over 2x cubed. And what's going to happen in the long run is that this is going to get really, really close to the ratio of 5 halves. If we let x get infinitely large, then that 3x and that minus 7 are going to become completely insignificant. And we're just going to end at 5 halves being that final answer right there. So because we had equal powers in the numerator and denominator right here, we ended up at the ratio of the constant coefficients of those two dominant terms. For the next one coming up here, we've got a 5x cubed over 200x squared. When we see these guys get simplified here, as x gets bigger and bigger, they become the dominant terms. It looks like this is going to be, what, like x over 40. Dividing by 40 means nothing when x gets infinitely large, so it looks like this one is diverging to positive infinity. We're going to use the words converge and diverge a lot this semester. We're talking about this one growing infinitely without bound. It is going to tend to positive infinity. It's going to diverge to positive infinity. We also want to remember here, we technically say that this limit does not exist. Technically, for a limit to exist, it needs to be equal to a number that we typically denote capital L. But it's really important for us to say in what way a limit does not exist. This does not exist because it diverges to infinity, as opposed to our last one right here. When we look at sine of x, we know that sine of x is just going to wobble up and down forever. It never converges towards anything. So our fourth one also does not exist, but it does not exist because of oscillation rather than divergence. So I will just abbreviate that as oscillating and abbreviate this one as diverging. There's multiple different ways in which a limit cannot exist, and it matters that we identify them. So because we're going to talk limits kind of a lot this semester, I just want you to know that it's really important. Unless the problem very specifically just says state if the limit exists or not, you really need to tell me in what way it doesn't exist if it doesn't exist. So again, for example, for the third problem in here, right here, this one where we got infinity, do not just say limit does not exist. You should be able to tell me limit tends towards positive infinity, negative infinity, whatever, or limit does not exist because it oscillates infinitely, stuff like that. So be sure to make those distinctions. All right, we're cruising here. Now we just want to talk a little Riemann sums, do a couple integrals, and we'll be all wrapped up. This Riemann stuff is super duper important. We're going to talk about a bunch of integration techniques this semester, and the most important thing for being good at integrals is being able to picture the Riemann sums that they come from. It's going to be a huge thing this semester. It's going to be an even bigger thing next semester when you all take 50C. Being able to picture Riemann sums is important. To me, again, this is not mathematically equivalent, but I think my analogy here is lots of people in algebra think that logarithms are annoying and inconvenient and difficult and hard to understand. And then in calculus is where you learn that logs are your best friend because they interact with exponentials, which is maybe the most important family of functions that there is. Logs have great properties, stuff like that. Like you learn to appreciate them over time. Riemann sums to me are that thing in Calc 1 where they are annoying to you in Calc 1. And then by the time you're actually a master of calculus, you realize that Riemann sums are the most sensible object and that you can't really live without them and that they help you all the time. You want to get there with Riemann sums. So you should stick with this thoughts about Riemann sums right here. It's going to help you out quite a bit for some of our more complicated ideas this semester. So for number 4 here, I've got a couple different parts. I've given you a basic Riemann sum. We're going to compute the Riemann sum approximation. We're going to compute the exact area, and then we're going to set up a third different problem right there. That's part C. So in part A, I'm saying to you, just do the R4 sum in this case, the right-hand Riemann sum with n equals 4 right here. So I'm seeing some things like A equals 0, B equals 2, n equals 4. So that's going to tell me that my width in this case here It's always our b minus a over n. It's going to be my 2 minus 0 over 4. This should be, you can just read this from the graph, right? I'm just trying to remind you about some of the notation that we use with some of this stuff right here. So I know that I'm going to have 4 rectangles. I know that the width of each of the 4 rectangles is 1/2. I know that the height of each of my rectangles is going to be based on the upper right corner. For this one, I can kind of cheat. I'm just going to look at the picture. For when we go to part C, we're going to have to actually compute some stuff right here. But in this one, it looks like we can do our, and you know, we just want our width times height, width times height, width times height, right? So this should be our sum of our width times our height in each case. In this case, we're going to get our width. This is our width in all 4 cases right there. So this should be 1/2 times the first height, looks like it's 0. Width of a half, second height is 1. Width of a half, third height is that at 3? Oh, we're doing x cubed. Oh, that's going to be 1.5 cubed. Okay, I'm just going to write that 1.5 cubed. And our last one out there is going to be, oh wait, was that point? Oh no, that was at 1. That's at 1.5. Height of 0. Height of 1, yeah. Height of the 1.5 cubed, and then we get our height of 8, yeah, out there. So 1/2 times 8, and that's 2 cubed right there. 1.5 cubed, 1 cubed. Oh, okay, sorry. This should be 1/2 cubed right there. That's 0.5 cubed. That's just going to be 0.125 right there, right? So we've got our Riemann sum right here. We've got our 1/2 times 0.125 plus 1/2 plus, and 1.5. What am I doing here? Let me grab my calculator real quick. 1.5 cubed and 3.375, and half of that. 1/2 of 3.375. And finally, we got a 4 out there. So I'm seeing here 0.06, what's that, 75, right? 0.6, what's your 625, okay. Plus 0.5 plus 3.375 divided by 2, 1.6875, and plus a 4. So what are we getting here? 4 plus that number plus 0.5 plus 0.0625, and I'm getting a total answer of 6.25 here. So 6.25, sorry, I'm running off my edge right there, 6.25. This is my R4 approximation. It's my right-hand Riemann sum approximation. In this picture, you should see that because this function is strictly increasing over the interval 0 to 2, that made our right-hand Riemann sum an overestimate. Our left-hand sum would be an underestimate. If we instead looked at 0 to -2 of x squared, oh wait, are we doing x cubed? Oh, we're doing x cubed, never mind. X cubed would end up being the same thing. X cubed is increasing always. Going backwards right there. I'll get this horizontal flip later here. So there we go. We got our part A. We did our Riemann sum right there. For part B, we just want to actually do the integral right here and see what the actual answer is. This is our approximation, right? This is our, and it's not a very good approximation, only an n of 4. Let's go ahead and actually do the integral now and see what we get. So when we do an integral from 0 to 2 of x cubed dx, remember this is saying we would like to take the antiderivative of x cubed, evaluate the antiderivative of x cubed at 2, minus the antiderivative of x cubed at 0. So we have to ask ourselves, if we took the derivative of something and got x cubed, what did we get? Well, I know that that when we're talking polynomial stuff, if I took the derivative of something and got x cubed, it must be something like x to the 4th, right? X to the 4th, the derivative of that gives me 4x cubed. I don't want 4x cubed, I want 1x cubed. So I only want to keep 1/4 of this right here. Now, if I were to take my derivative here, the 4 would cancel with the 1/4 for a 1, and we'd be left with x cubed. So this is my antiderivative of x cubed. I'm going to evaluate this from x equals 2 to x equals 0. Another thing I'm going to say here is you should absolutely be writing x equals and not just 0 and 2 right there. We're going to have a whole mess of different variables that we're integrating over the semester, changing variables. Multiple different sections involve change of variable. It matters that you're keeping track of which variable we are discussing right here. I know that these are x values 2 and 0 because this was dx. I'm going to make sure that I keep track of this being x. There's only x's in this problem. There's going to be other things later. This is just good practice right here. So I can go ahead and evaluate this now. This 1/4 is a constant multiple, so I can always just let it ride out front. We're going to get 2 to the 4th minus 0 to the 4th for our evaluation right there. And so 2 to the 4th is 16. 1/4 of 16 is 4. So I knew that this was an overestimate before. And we can now see that it certainly was an overestimate, and by kind of a lot. This is really a terrible estimate right there, but again, our 4 is a terribly small number of breakdowns right there. This is with an infinite number of rectangles that were infinitely thin. We actually get exactly an area of 4 underneath x cubed from 0 to 2 right there. So there's our exact answer for what the Riemann sum was estimating. Now let's go back and do one other Riemann sum right here. So part C technically has nothing to do with what we've previously been doing in this problem. It should just be sort of like a mimic of the previous parts here. So what I'm thinking here is I want the L6 estimate over the interval 0 to 3 for the function x squared. We were dealing with x cubed before. We're dealing with x squared now. So I'm picturing for myself. Let me see how bad of a picture I can go ahead and draw here. Picturing our x squared function. We're going out to 3. I know that I want 6 subdivisions here. We're doing our left-hand sum, so I know that I'm going to be looking at each of my left points right here. So I know that before, notice that when we did our right-hand sum, 0 was not a used x value. 0.5 was our first visited x value in our interval because that was a right sum. In this one, we will disclude our last value right here, and we'll only use our first. Notice here, there's actually 7 dots that I drew. The left sums will use the left 6, the right sums will use the right 6. So it's only the end ones that change. So I guess my rectangles here are going to be this one that's at a height of 0. This one, we'll figure out their heights here in a minute. But we should be doing left sums. So here's all my left sum rectangles here. And man, being able to draw this picture really matters. We're going to draw a lot of these pictures this semester, and I'm going to ask you, I'm going to say, what does your Riemann diagram look like? This is my Riemann diagram. It's helping me figure out what all of my pieces are actually going to be. We're going to try to find areas and volumes of much more complicated things this semester, and it matters that we can picture our Riemann diagram of where each of these pieces are at. So what I'm picturing here is I know that since this is from 0 to 3 and we're doing 6 subintervals, I can clearly see that my delta x is again going to be 1/2, right? 6 steps broken up over a width of 3. It's a half of a unit for each step right there. All I've got to do is identify what are each of my heights going to be out here. I know that my x list here is going to be each of the x values that I'm going to use. We're starting at 0 and increasing by a half each time. So I'm going to be bad and use mixed fractions right now, but just to help kind of visualize it. And notice here, my 6 heights are, we didn't get to 3, right? 3 got discluded. If we were doing R6, 3 would have been included and 0 would have been discluded right there. It's which endpoint are we including here? Again, notice we are expecting to get an underestimate for our solution right here. So let's go ahead and do our Riemann sum here. This should just be the sum of the widths times the heights again. Here, this should be, the width is 1/2 in every case, since it's constant. And so I'm just going to rewrite this as saying this should be 1/2 times the sum of the heights, because it's 1/2 times a thing, plus 1/2 times a thing, plus 1/2 times a thing. So last time I wrote that out kind of a dumb way right there. So let's see. Sorry, I'm going to move back to the side a little bit over here so we can see this. So I'm going to just do here 1/2 times, and I'm just going to write out my 6 heights right here. First rectangle height is 0 squared for 0. Second rectangle height is 1/2 squared for 1/4. Maybe I'll just do these without the squares on here. The next one is going to be, and again, I guess I should be looking at this. It's the sum of the squares of all of these. So 1/2 squared is a 4th. 1 squared is going to be 1. 3/2 squared is going to be 9/4. Gosh, why did I write those as mixed fractions? 2 squared is going to be 4. 5/2 squared is going to be 25/4. And so that 0 doesn't even matter right there. Maybe I should get these in terms of fourths. 1/4 plus 4/4 plus 9/4 plus 16/4 plus 25/4. So it's really just the sum of squares in the numerator divided by 4, and we're going to multiply the whole thing by a half. And so what are we landing at right here? It looks like we've got a denominator of 1/8, or denominator of 8, I should say. And what do we have up in the numerator? 5 and 25 is 30. 9 and 16 is 25. And so 55 in the numerator. So 55/8 looks like my L6 approximation right here. So I'm just going to say this one more time here. Doing this Riemann sum is annoying, and doing almost all actual Riemann sums is almost always annoying. I would rather we wrote computer programs to do the Riemann sums, but thinking in terms of Riemann objects, the rectangles that we're thinking of right there, that we all picture that situation had 6 rectangles, but obviously the goal of calculus is to say, but what if there was an infinite number of rectangles? We want to be able to picture that rectangle, and for me to say my generic Riemann object is a rectangle of width 1/2 of height based on the function x squared. Being able to picture that that is our Riemann object that we're adding up an infinite number of, that's what's really helpful to me right here. So again, doing these, if you're annoyed, good. We don't want to necessarily do a ton of Riemann sums this semester, but we need to be able to think in terms of Riemann objects here. Drawing pictures like this is going to be a picture that we're going to do kind of a lot of. Doing math like this is something that we're going to try and avoid doing out here. Okay, so we're done with Riemann. Let's go on to some integrals and we'll be done here. So for number 5 right here, we're really just looking to remember, I'm going to rethink about that statement that I said, the integral is the area under the curve. That is the sentence that's going to get me through this problem right here. I'm asking you to compute a bunch of integrals. I've given you a piecewise function. The piecewise function's graph happens to be a circle, then a rectangle, then a triangle. You can see in my graph those dashed lines. Those are just indicating, I mean, that's not part of the graph. The graph is only the solid line right there. Those are just kind of indicating that the graph does just drop off right there. All right, so we want the areas that we're looking at here. So this should just be our first one. Integral from 0 to 2 of the function says how much area is underneath the graph from the x value of 0 to the x value of 2. What I can see in this case is that that is just a quarter circle. That's the area that we're accumulating right there, because that's our x value of 0 and that's our x value of 2. So I just need a quarter of a circle's area. That circle has a radius of 2, so I know that the entire area is going to be pi times 2 squared. There's pi r squared, that's 4 pi. I only want 1/4 of the area because we just have a fourth of a circle, so that should just be pi. So our answer for the first one is pi, because that is 1/4 of the area of a circle of radius 2. For the second one here, we're going integral from 0 to 7. And so the integral from 0 to 7, the other way that I kind of might, well, okay, we have the entirety of the half circle, and it looks like we're going to get also the first half of that rectangle right there. So to me, this, I'm going to just notate this as the entire one of those plus, and it looks like we're going to get half of that rectangle. Actually, that, oh no, it's almost a square. Never mind. Okay, so we're just going to get here that this is going to go from 0 to 4 now, and that's at 2. And over here, we've got that this goes from 5 to 7 right there. Further, this has a height up here of 3, maybe, is our overall height for this guy. So again, we're just doing areas. So I want now, we had a quarter of the circle as pi, so it should be that half of the area of the circle is going to be 2 pi. That's one of my parts. It looks like our rectangle area is 2 times 3 is going to be 6 units in the piece of the rectangle that we got. And so for my final answer here, it looks like our integral value is 2 pi plus 6. The area underneath our function between our curve and the positive x-axis is 2 pi plus 6. It's the entire half circle plus half of the rectangle. For the next one here, we're going 5 to 12. So 5 to 12. 5 to 12 is basically saying to me the whole rectangle, the whole triangle. The whole rectangle, the whole triangle. The whole rectangle has a width of 4. This is going to be 4 times 3. That's going to be 12. Plus the triangle's formula, 1/2 base times height. The base width is 2. It goes from 10 to 12. The height is 4. And so it looks like the entire triangle's area is going to be 8. Half of 8 is 4. So it looks like our next answer here is going to be 16. And finally, the last integral here says let's go from positive to negative infinity. Well, we're really just going to grab the pieces of our previous parts right here, right? So this says integral from negative to positive infinity. So this just says, give me the whole thing. Give me all the area under all the parts from negative to positive infinity. Well, we know this, by the way, I'm just going to say this should be equal to the integral from 0 to 12, right? Because there is no other area under the other parts. There are no other parts. The function looks like it only exists there. So this would be the same thing as this in this case, because we're not accumulating area in any other region other than 0 to 12. So I'm just going to say this is the semicircle, this is the rectangle, and this is the triangle. The semicircle's area we determined to be 2 pi. I'm just referencing that from when we figured it out here. The rectangle's and the rectangle plus the triangle is 16. I know that from the previous computation. So that's all I got to do to get our last one right there. Just add up previous parts that we've already seen, 2 pi plus 16. So again, notice that an integral does not necessarily mean do calculus. Integrals ask for areas or volumes, depending on what dimension that we're in. You can do geometry if there's geometry available to be done. As soon as you see shapes that you recognize, and I mean, there's the 3 shapes that you recognize, circles, rectangles, triangles, then you should maybe just do geometry. All of the shapes, even areas under things as natural as x squared, x cubed, those are a little bit weirder. We got to do calculus for those. So let's go ahead and look at a couple definite and indefinite integrals, and that'll be the end of this guy here. So just do 5 more, and we're done. So next parts that I'm looking at here, we're just going to do some integrals. Remember, an integral is an antiderivative. So we're going to remember that we want to just be able to think backwards here. So first one that we're looking at here, the indefinite integral. It's not definite because we don't have bounds. We just want to know a general function that this works for here. And we're getting x squared dx. So we want to know, if I were to take the derivative of something and get x squared, what did I take the derivative of? It's got to be that it was something x cubed, because we know that if derivatives reduce the power by 1, integrals must increase the power by 1. I don't want to get 3x squared when I go back to take my derivative, though. I only want 1x squared. So I'm only going to keep 1/3 of this right here. So now when I take my derivative here, I'm going to get the 3 is going to cancel with the 1/3, and we're going to be left with x squared, which is good. The other thing that we need to remember is that we're asking the question, what could I have taken the derivative of to land here? And the point is that you should also see is there could be any constant out here. If this was plus 10, then when we took our derivative to go back to the left, plus 10 would just go to 0. It's a constant, right? So what we need to remember is that derivatives and integrals are almost perfect inverses of each other, but not quite. The one way in which they're not perfect inverses of each other is that when you integrate, you always pop out this plus c on the other end, because there could be any amount of vertical shift. You can't identify vertical shift if all you're measuring is the slope of a curve. Slope of a curve does not depend on how high up or down that curve lives in the plane. So that plus c is saying there's actually an infinite number of functions that all have a derivative that leads to x squared. But that's really just because constant multiples all go to 0 right there. So there's our first one, 1/3 x cubed plus c. We get a plus c because this is a indefinite integral, as the first 3 are. Next one here, x times x minus 3 dx. This one here, we want to remember, just like with differentiation, you can't just go plowing into these. The derivative of the product is not the product of the derivative. We have a special product rule. Unfortunately, there is no product rule for integrals, but the good news is I can just multiply this guy out. Mostly in life, man, I really prefer polynomials in factored form, except for when I'm doing calculus. And calculus is better to be in standard form here. So that I can just do this piece by piece. So now I can see we just did, okay, actually, sorry, let me rewrite this a little bit right here. We do get to split up our integrals over constant multiples and stuff like that, and over addition and subtraction. So I can a little bit more simply rewrite this for myself like this. We're going to reuse our old answer from our previous problem a second ago. This should be 1/3 x cubed over here. The integral of x, well, if I took the derivative of something got x, it must have been something x squared. But I don't want the 2x squared. I only want, and I'm ignoring the 3 for right now, I only want 1x squared, so I'm going to keep half of that. So 1/2 x squared. Certainly we'd rewrite that as 3/2 x squared. I'm not going to write that right there, but there we go. I almost forgot the most important thing. Don't forget your plus c's. I'll harass you about it quite a lot. In your online homework, you'll see that some of the problems build in the plus C like next to the text box so you don't have to type it. Some of them don't, and they'll tell you that you're wrong if you don't include the plus C. So always stop and think, does that deserve a plus C? If it's in terms of x, the answer is yes. If we have definite integrals, then the answer is no, because we'll do subtraction and the plus C's will cancel. So let's do one more, and then we'll see our definite integrals here. We get our sine of pi x. Now we're going to come up with a rule for this. The point here is that we sort of need a chain rule, and we probably, I'm assuming that you did not get to the reverse of the chain rule last semester. That's section 5.4, 5455. So we're going to kind of start with that this semester here, but we can at least think about this one. We can always trial and error our way through these simple chain rules here, but we're going to want the rule for the more complicated ones. So here's the thing I'm thinking. I want to take the integral of sine, so I'm going to think about derivatives of sine to help me work backwards. I know that the derivative of sine is cosine. The derivative of cosine is negative sine. So I'm thinking to myself, this should be like a negative cosine of pi x, because the derivative of cosine is negative sine. When we pop out the negative from taking the derivative, it'll cancel with this negative and leave us with a positive sign. Our only issue now is if I took this derivative, I'm going to get positive sine, which is good, but I'm also going to pop out a constant multiple of pi, which I don't necessarily want, right? So I'm only going to keep a 1 over pi fraction of this. That way, when I take my derivative, negative cosine is going to go to positive sine. The chain rule will pop out a constant multiple of pi, and pi divided by pi will cancel, leave us with one copy of sine of pi x. So a lot of times, as you've been watching me do right here, I stop and I think about my essential part of the function. I say to myself things like at the very top of my screen, the integral of x, well, it should be something x squared. Then I go figure out my constant multiple. I'm doing the same thing with trig functions. Sine, well, it must have come from a negative cosine and of the same parts, right? Then I go figure out my constant multiples at the end out there. So I do like to think that guess and check is sort of a thing that, in a sense, I want you to know what you're doing. So guessing and checking sometimes makes it seem like you don't know what you're doing. But in a lot of cases, I know for a fact that guess and check will be a viable method to the solution. So you should kind of start to reopen your mind to guessing and checking actually being more of like one of the fanciest techniques that we do, rather than it being what you do when you don't know how to do. Half of differential equations is being a smart guesser rather than developing accurate techniques. It is a high level kind of thing, like being a smart guesser and checker matters. So keep doing that kind of stuff right there. That is a good approach for these. So that was our 3 indefinite integrals. They were indefinite because we were not given bounds over which to evaluate them. This is just a general integral. We could apply bounds to the antiderivatives to find some areas. That's not what happened in the previous 3. In the next 2, we now actually are given some bounds over which to evaluate these. So these are our definite integrals. So we still want to do step 1 is find the antiderivative, but now step 2 is going to be evaluate the antiderivatives at the upper bound minus the lower bound. So here we're going to do some antiderivatives. What do you take if you take the derivative of something and get 1, what was it? Well, that was just x. The derivative of x is 1. You took the derivative of something and got 1 over x, what was it? That's going to be the natural log of x. So that is my antiderivative. In this case, I don't need a plus c, because what we're about to do is we're about to evaluate this from x equals 1 to x equals 5. To do this, we're going to evaluate the antiderivative at 5 minus the antiderivative at 1. If we stuck the plus c's on here, we would just have a plus c minus a plus c again on the other end, and they cancel. That's why we get to ignore our plus c's on our definite integrals right here. They are there. They just are guaranteed to cancel every time. So we get our terms, our upper bound parts. That's going to be 5. That's not a decimal right there. 5. Oh, not still pressing. Okay, here we go. All right, we're okay. There we go. 5 minus natural log of 5. That's nothing. I just don't want to go back and erase that. Minus 1 minus natural log of 1. You should know what the natural log of 1 is. You shouldn't have to go look in a calculator. You should know what the natural log of 1 is. I'm going to draw a picture for you in a minute. If you don't know the natural log of 1, and if you don't recognize my picture, then if you are 18 years old, you are required to go out and get this picture tattooed on your body, because it's not acceptable for us to not know our basic e and natural log value. So here we go. We should be getting here 5 minus natural log of 5 minus 1 It looks like we're going to distribute here. This should be a plus. That's a 0. Natural log of 1 is 0, and you should know that because e to the 0 is 1. So natural log of 1 is 0. They're inverses of each other. So it looks like our final answer here is 4 minus ln 5. The picture that I expect every single Calc 2 student to absolutely have burned into their brain is, okay, I'm doing it bad. All right, don't use my doodle when you go to the tattoo shop. Oh man, I'm just gonna have to redo that one. But you should all know e to the x, natural log of x are inverses of each other. The two most important points on this graph are 1, 0 and 0, 1. This is our e to the x. This is your natural log of x. Don't forget these pictures. These tell you so much information about like the most useful families of functions that there are. You only even need to know half the picture because it's a mirror image over itself. You absolutely should know your basic natural log values. Natural log of e is 1, natural log of 1 is 0. And the reason that you know it is because you're going to go get that graph tattooed on yourself right now, given that you are able to do that, because you should know those. Let's go ahead and do our last one here, and this will be the end of the refresher here. Our last one here, we got a trig. We've got a definite trig right here. I don't know, a little bit lazy on my part. I don't know why I'm evaluating trig things over non-pi based bounds right here, but whatever. I took the derivative of something and got cosine. What did I take the derivative of? Well, that one's pretty easy, just sine of x right here. And I'm evaluating this from x equals -5 to x equals +5. And so this should just be sine of 5 minus, what was that? Minus, so it wants to go back again. I don't know why I gotta press both ways. Minus sine of -5. And by the way, we should be able to do a variety of simplifications here. In a sense, we're done right here. In a sense, you're technically good and this is the final answer. But there's a couple smart things that we should stop and think about for ourselves because these bounds are symmetric. A couple things. One, I know some trig properties that allows me to rewrite this. This is really plus sine of 5 because the negative on the inside of a sine does pop to the outside right there. That's one of our properties of sine. If this is a cosine, cosine of negative theta is the same as cosine of positive of that theta with a cosine. The cosine can just eat that negative. So it looks like this is actually 2 sine of 5. The other reason that I knew that I was going to get 2 sine of 5 right here is because I know that cosine is a graph. Cosine is, oh my gosh, okay, whatever. It's supposed to be, right there, right, whatever. So the point is, this graph matches exactly on the left, whatever it has on the right. So the other thing I'm thinking to myself right here is that since this graph has horizontal symmetry and our bounds are horizontally symmetric about 0, I could instead rewrite this integral as 2 copies of the integral from 0 to 5 of cosine of x. And I know that because this right-hand half is equal to the left-hand half. So I can just do 2 copies of the right half over here. And if I did this, come on, computer, keep up with me. I'm going to get sine of x again. I'm going to get 2 sine of x. It's going to get evaluated from x equals 0 to x equals 5. And now I'm just going to get 2 sine of 5 minus sine of 0. Well, sine of 0 is 0, and we're just going to get 2 sine 5 again. So do remember that you know things about functions. So again, just like we want to say sometimes integration is just geometry, sometimes integration also, the technique that you use depends on what function you're integrating. When we stop and think about these graphs, it often gives us extra pieces of information. Maybe the last thing that I should say is this. Let's do one more right here. I'm just going to tack on to the end. If you're sitting here following along, great. If I were to instead do -5 to 5 of sine of x, then what's the answer going to be? And rather than do calculus, I'm just going to think about it. I know that sine of x is different than cosine of x. I know that sine of x is a mirror image, but always top-bottom mirror image as well. That means that whatever positive or negative area I accumulate on the right, I'm going to accumulate the opposite of that on the left. Therefore, since this accumulates area in equal amounts to the right and the left of 0, whatever positive or negative area it accumulated from 0 to 5, it accumulated the opposite of that from 0 to -5. And so this has to be 0. And it has to be 0 simply because sine is an odd function. Odd functions evaluated over symmetric boundaries is always going to give you 0 because the left and right sides are always going to cancel out when we cross over 0 right there. So again, I don't have to do the calculus right there. I'm picturing the graph. I've got other ideas that help me do integration. And so yeah, maybe that's just my last statement for this refresher right here, which is integration is one of the most classically difficult things in math. It's not like you just get good at it. With derivatives, we just end Calc 1 being like, you can take the derivative of everything now. That doesn't happen with integration. Integration never gets to be a point where you can just do all of it. And so it matters that we always think about little tricks that help us avoid actually doing the calculus. If we can think geometrically, if we can think in terms of Riemann sums, if we can think about symmetries, all of these things are going to help us avoid truly doing the calculus step. And the calculus stays hard. It doesn't get easy. We're going to learn a bunch of techniques this semester, but like most of them are not straightforward and you don't see it immediately. Like this is always something, if we can avoid it, we should. And so always stop and think. Don't go plowing into doing calculus if you can stop and find an easier route to this. So I think this is the wrap up to my refreshers right here. I think I got all these. Again, I'm just going to say the words that are sitting down here. You should go ahead and use these resources to check your answers. By the time you're in Calc 2, you are certainly expected to basically be able to confirm almost every answer from the entire semester that we're going to get. This semester we will do a couple like proof-based things that'll be a little bit harder for you to verify for yourself online, but you're not just taking classes and getting lectured at anymore. You should be more independent in your ability to come up with your own stuff here. And so if you're not used to using Desmos and Wolfram to just look up, confirm all of your answers, you should spend a lot more time at those two websites playing around with things and seeing what kind of capabilities they have, see what ways you can help yourself out with those types of things. So play around with those. I hope this video is both viewable and hearable here. I guess I'll verify that in a second. And yeah, if you have any questions about this, certainly go ahead and send me an email. And otherwise, I'll see you guys next video.